Okay, for this lesson, we're going to continue on with our derivatives, and we're going to look at how to sketch these derivatives. So to sketch a derivative of a function, we must understand that we're sketching the x value of f against the slope of the tangent line to f at x. No, when we're sketching the graph of f prime, we are only concerned with getting the correct shape. We're not concerned with finding the exact points besides the x-intercepts, which we're going to take a look at how to do in a second. So we're looking at the shape of how it changes, not about does it exactly match with this value at this point. When we're sketching the derivative functions, so on the original graph, draw in all horizontal tangent lines. These lines are going to be the points where it has a slope of 0. So we graph these x-intercepts of the derivative. So when we have a horizontal tangent, the slope is 0, that's an x-intercept of our f prime. Next, if the graph of f of x is increasing over an interval, the derivative function values will be positive because if it's increasing over that interval, then it has a positive slope. If it is decreasing over a set interval, then the derivative function values will be negative. And for polynomial functions, the degree of the function is always going to be 1 less than the degree of f of x. This means, as we've learned in previous courses, that there is 1 less turn in the derivative graph as compared to the graph of f of x. So let's take a look at our first one. Now, we know that this is just a quadratic. So we can see that in this case, we have f of x has a degree of 2. That means that f prime of x has to have a degree of 1, which we know is linear. Then we take a look, and we can see right at this vertex here, it's going to turn, and it's going to have a slope of 0 right at the vertex. So this f vertex is going to be, as we talked about, an f prime x-intercept. So when we have that horizontal line or that vertex, suddenly that's going to be an x-intercept on my f prime. Then if I'm looking to the left of that, I can see that my original one is decreasing. Well, if it is decreasing, then that means that my slope is negative. If it is increasing after the vertex, then my slope is positive. Which means that I can state if f is decreasing, f prime is negative. Or if f is increasing, f prime is positive. When I look at my second graph, I can see that this has 2 turns in it. I can see that at the peak of those turns, I'm going to have a slope of 0, which means that at those points, I'm going to have an x-intercept. I also have this turning point for the curve, which we're going to call a point of inflection. This can occur as I am increasing, or I can have it occur like this. And what you see is along the curve, I'm going to have some point of inflection halfway between where the 2 vertices occur, where in one case I can see that this is coming up and this is going down, and in this case I can see that it's increasing going down, it's increasing going up, and that's reflective of my change in the slope, or more specifically, my change in how steep that slope is as it changes. So when I look at this curve line running through here, then I have a point of inflection which occurs here. Now, why is this relevant? Well, what you're going to find is we know that we have the 2 x-intercepts that go through here and here, and that as this is coming through, it's all a negative slope here. But because this has a degree of 3 and it's going to a degree of 2, what's going to happen is at that point of inflection, my vertex of my quadratic is going to occur. Where we can still see that because throughout this entire section, my slope is going downwards, it's still going to go downwards through all that point, but it's going to have its steepest point or steepest slope right here, and then it's going to have a less steep slope to the left and to the right of it, even though it's all still negative, which is why I have that vertex of my quadratic occurring there. So those points of inflection are going to help us shape the graph. Remember, it doesn't have to be perfect, but we are going to have the general shape of the graph. If we apply the same principle to example C, we're still doing the same idea where I have those points those maxes or mins where my original graph, or sorry, my f prime is going to be 0. Those horizontal slopes, f prime at 0. The second thing is we're looking for those points of inflection, those steepest points, and we can see them occurring approximately here, here, and here. And what's going to happen is, as this is negative, it's going to come down, hit its lowest point, and then come back up. And then this entire section here is all positive. So it's going to come up, hit its highest point at the point of inflection, and then come back down. And the pattern is going to continue. And then it's just going to keep going. And we're going to get something like that. For example D, we can see that even though my values for f of x are always positive, the same thing is not necessarily true for my f prime. Even though this entire graph is above the x-axis, I can see that I have a section here and here where I have a negative slope, and here and here where I have a positive slope, which means that my f prime should be reflective of this. So I'm going to start with those x-intercepts. And we can even see, because the x-intercepts or the vertices happen on that x-axis, the x-intercepts are going to be the same for two of them on the f of x as the f prime of x. I'm going to find my points of inflection here and here. And then I'm going to have one x-intercept that is not going to match up with my original graph. And I'm going to state where there's a negative slope, this is going to be negative. Where there's a positive slope, this is going to be positive, and it's going to turn at that point of inflection. It's going to be negative and turn at that point of inflection. And it's going to shoot off into infinity.